Welcome to the class. Dear students, today we are going to discuss on Lewis acids and Lewis bases. So first we will discuss Lewis acids. We will discuss the introduction and then we will look into the examples to better understand what is Lewis acid. And then we will look into Lewis base and a short introduction, and then we will look into the examples of Lewis bases. And lastly, we will see some examples of reactions which involve both Lewis acid and Lewis base. So let us start the class. Lewis acid. Lewis acid is a substance that can accept a pair of electron. Lewis acid can accept a pair of electron. And why does it accept a pair of electron? Because it has got an empty orbital. Okay, all because the atom has got empty orbital, it can accept a pair of electron, and because of acceptance of this pair of electron, it is referred to as Lewis acids. So the reason for acceptance of a pair of electron is actually an empty orbital. Okay, so substances that can accept a pair of electron, they are Lewis acid. And why? Because why does it do so? Because it has got an empty orbital. An example of Lewis acid is FeBr3. We have seen this example in Friedel-Crafts alkylation. In my earlier videos, I have discussed about Friedel-Crafts alkylation and how FeBr3 accepts an electron, okay, from Br- and acts as Lewis acid catalyst. Please refer to my earlier video. Here, in short, I would tell you that it accepts Br- and becomes FeBr4- and Br+, that is the electrophile, comes out, as you can see here. So FeBr3 accepts a pair of electron, and exactly why does it accept so? Because Fe, that is iron, has got empty orbital. What kind of empty orbital has iron got? We will see that when we discuss examples. So let us discuss examples of those substances that show characteristics of acceptance of electron or that act as Lewis acid. The first example of this is H plus H3O plus. H plus, what is the orbital of H? S orbital. Okay, H, it has got one electron. What about H plus? No electrons, but the orbital is still there. So H plus has got an empty 1s1 orbital. So it can accept a pair of electron, right? So therefore it is a Lewis acid. Let us now discuss about S3O plus. Where is the positive sign? On oxygen. What is the atomic number of oxygen? 8. Can we go for its electronic configuration? 1s2, 2s2, 2p4. Right? Shall I draw this? It would be like this. Right? What is the oxidation state of oxygen? -2. 2 valence electrons are there. So if 2 comes, it would complete its octet. Right? So let 2 come, let it combine with 2H to form H2O. So when it forms H2O, its octet is complete. Right? When does it form H3O plus? When H plus attacks the lone pair. When H plus attacks the lone pair, this orbital becomes empty, right? And then this orbital can accept a pair of electron. Okay, therefore H3O plus acts as a Lewis acid. You got it? H2O as is no problem, because when it becomes H2O, oxygen is able to complete its octet. But when H plus consumes this lone pair of electron into its orbital, this orbital, that is the 2s2 orbital, becomes empty. The 2s orbital becomes empty, and because of this empty orbital, it acts as a Lewis acid. What I mean to say here is that the Lewis acid, what we call as a Lewis acid, should have an empty orbital in order to accept electron. Or then only it can accept a pair of electron, and then only it can be termed as a Lewis acid. Now let us understand this better by going to the second set of example. P block elements. P block elements, atom that belong to P block elements. So in this atoms that belong to p block elements are boron, okay, iron, aluminum, zinc. See, all of these, be it boron, iron, aluminum, zinc, they are all Lewis acids in compound form, not in ionic form, but in compound form they act as Lewis acids. How and exactly why does it act as Lewis acid? This we can see by taking the example of BF3. What is the atomic number of boron? 5. How many electrons in first shell? 2. How many in second shell? 3. So what is the valency of boron? 3. 3 valence electrons are present in boron. So I am going to draw boron like this. Fine. Now let us take fluorine. What is the atomic number of fluorine? 9. And what is the 2 in the first shell and 7 in the second shell? So what is the valence electron of fluorine? 7. Let me draw for fluorine. This is for fluorine. 7. Now let us combine B and F3. How many electron does B require? Boron requires 5 more electron to complete its octet, and fluorine require 1 more electron to complete its octet. So let us go for a covalent bonding. Now what happens? These are the 3 valence electrons of boron, and here is our fluorine. By making covalent bond with boron, what does fluorine gain? Fluorine gains its octet configuration. By making covalent bond with boron, look at this. By making covalent bond with boron, fluorine is getting its octet configuration. 1, 2, 3, 4, 5, 6, 7, 8. It's for all the 3 fluorines that they obtain their octet configuration. But what is the case of boron? See, 1, 2, 3, 4, 5, 6. So it has not obtained its octet configuration. How many are required more? 2 electrons are required. Therefore, BF3 acts as acceptor of a pair of electrons. Therefore, BF3 acts as a Lewis acid. Therefore, BF3 acts as Lewis acid because it wants to complete its octet. Now let us see the same thing using iron. Okay, FeBr3. Let us prove for FeBr3. What is atomic number of iron? 26. Can we go for its electronic configuration? 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d6. Look at its outermost shell. Which is the outermost shell here? This one. How many electrons are deficient? 2 electrons, right? For becoming octet configuration. So it accepts as acceptor of electron. It acts as an acceptor of electron. If it takes a pair of electron, it would be able to complete its octet configuration. Therefore, iron in compound form acts as acceptor of electron. That is, it acts as Lewis acid. Similarly, in the same case, you can see for AlCl3 and zinc chloride also. Let us see other set of examples and we will get a better idea. Block 15 elements, atoms that belongs to block 15 elements, PCl5 and bismuth pentafluoride. PCl5, what is the atomic number of phosphorus? 15. Can we go for its configuration? 1s2, 2s2, 2p6 and 3s2. How many now? 10, 12 and 3p3. 3p3. What about the d orbital? There is a d orbital in the third shell having, see, 1, 2, 3, 4, 5. D orbital can take 10 electron. What about that d orbital? Correct? So when it is in excited state, when phosphorus is in excited state, this electron would jump here. Correct? What about these orbitals? They are empty. What I mean to say is that orbitals are empty, that is why they are able to accept a pair of electron and act as Lewis acid. So PCl5, we are seeing that the 3d orbitals are empty. Similar is the case of BiF5. You can see for bismuth, its atomic number is 83. So you can see. Let us see another set of examples to understand this same thing again and again. Compounds that can form coordinate covalent bonds with water. Coordinate covalent bonds with water. Let us see which atoms can form magnesium. Okay, lithium. What is the atomic number of magnesium? 12. Can we write its electronic configuration? 1s2, 2s2, 2p6, 3s2, right? So how many now? 12. What about 3p, right? And 3d. Okay, these are 1, 2, 3, 4, 5. That's right. 1, 2, 3. 3p and 3d. See, these are empty orbitals in the third shell. Okay, in the third shell, these are the empty orbitals that are there. So magnesium, it can accept pair of electron from oxygen of water, right? So it will act as a Lewis acid catalyst. Similarly, lithium, it is having atomic number 3. It is having atomic number 3. So its formula will be, electronic configuration will be 2s1. What about 2p orbitals? These are empty. Correct? So here also we can see that there are empty orbitals for lithium and that it can accept a pair of electron from the oxygen of water. So all this magnesium, lithium, it also act as Lewis acid catalyst, Lewis acids. Let us now see another example of Lewis acids. Another example of Lewis acid, carbocations. Carbocations. We know three kinds of carbocation, right? What are they? Tertiary carbocation, secondary carbocation, primary carbocation, ethyl carbocation, and methyl carbocation. See, all of these carbocations have got empty what orbital? sp3 hybrid orbital. Empty sp3 hybrid orbital. So they can accept a pair of electron. This one, there are 4 orbitals. There are 4 sp3 orbital. One is empty, vacant. So here it can accept a pair of electron. So therefore, carbocations, because they have got empty sp3 hybrid orbital, they also act as Lewis acid. Here also there is one empty sp3 hybrid orbital. Here also there is one empty sp3 hybrid orbital. So they all act as Lewis acids. What we are again highlighting again and again is that Lewis acids have got empty orbitals which can accept a pair of electrons, and therefore they act as Lewis acids. Now let us go for Lewis base. Lewis base. It's just the opposite of Lewis acid. Lewis base donate a pair of electron. Substance which can donate a pair of electrons are called Lewis acids. Donate a pair of electron, they are called as Lewis bases. Okay, let us look at an example. Let us take the example of primary amine. Yes, I know it's a Lewis acid. See, the nitrogen can donate a pair of electron to the Lewis acid here, and here you go. Yes. Now because the H plus proton here, it has taken a lone pair of electron, the nitrogen here atom has become positive. So which has donated, what has donated the pair of electron? Primary amine. So this is a Lewis base. That which donates a pair of electron is a Lewis base. that which accepts a pair of electron is a Lewis acid. Let us understand Lewis base more by looking at its examples. Let us look at its example. The first example, and one of my favorite, is ammonia and amines. Ammonia and amines. So ammonia, let us look at ammonia, NH3, amine, primary amine, secondary amine, tertiary amine. Look at the lone pair of electron in nitrogen. Nitrogen atomic number, what is it? 7. What is its electronic configuration? 1s2, 2s2, 2p. 2p, how much will come? 4, 3. Correct? Can I draw? Let us draw it and see. This is the 2s orbital. So here we can see that nitrogen has 3 valence electron. It can take part in bonding. So there are 3 bonding electrons in nitrogen. And there is one lone pair of electron in the outermost shell. That is the 2s2. 2s2 lone pair of electron. So because it has got lone pair of electron in the outermost shell, it can donate the lone pair of electron, and therefore it can act as a Lewis base. Therefore ammonia, primary, secondary and tertiary amine act as Lewis bases. Why? Because they have got a lone pair of electron in the 2s2 orbital. Similar, in the second example of Lewis base is pyridine and its derivative. And why pyridine we know, because its reasoning we have already given. It is also having nitrogen, that is why. Pyridine and its derivatives. Look at this. Pardon me, this one and nitrogen. Yes. Look at the lone pair of electron on nitrogen. Let's draw nicotinic acid also. Look at the lone pair of electron on nicotinic acid. So because it has got lone pair of electron on the 2s2 orbital of nitrogen, therefore it is able to donate its electron pair and therefore act as a Lewis base. Let us see the third example. Group atoms belonging to group 16 or group 16 elements. Let us see group 16. Group 16 is oxygen family. Okay, so we are going to write compounds of oxygen, H2O, your alcohol, your ketone, aldehyde, ether. See, look at this. There are 2 lone pair of electron in oxygen. Oxygen, what is atomic number of oxygen? 8. What is its electronic configuration? 1s2, 2s2, 2p, 4. Let us draw this. So we can see that oxygen has having oxidation state of -2. Okay, it needs to give or take 2 electrons to get the octet configuration. Lone pair of electron, there are 2 lone pair of electron in the outermost shell. One is this and one is this. Correct? So it has got 2 lone pair of electron on its outermost shell. One is the 2s2 and one is the 2p2. Correct? So it has got 2 lone pair of electron. However, it will only donate 1 lone pair of electron. Okay. So if H plus is coming, then it would take this pair of electron and it would become H3O plus. A lone pair of electron here remains. However, if another H comes, it would not be able to attack this lone pair of electron because already there is H here that has taken a lone pair of electron and it is providing steric hindrance to this incoming H plus. Why I am saying like this is because the molecule of water is in itself is very small. H2O molecule in itself is very small. So that when H comes and attach, H is also very small, but because the molecule of water is very small, H has significant impact on the steric hindrance. So if H plus is coming and taking one lone pair, it provides enough steric hindrance to prevent another H plus to attack the lone pair of electron. So, and because this one more thing is the lone pair of electron is on the same atom. So that's why another H plus would not attack it. Okay. So only one lone pair of electron is taken from oxygen. So you can see oxygen's two lone pair of electron. Because of that, it is able to donate the one lone pair of electron, and it is able to act as a Lewis base. Similar is the case with other group 16 elements like sulfur, hydrogen sulfide, dimethyl sulfide. Similar is the case for selenium, tellurium. Okay, all these compounds have got two lone pair of electron, and they donate one lone pair of electron to act as a Lewis base. Now let us see another set of example. Simple anions that have got lone pair of electron. Simple anions that have got lone pair of electron. These are very simple anions. See, F minus, it has got a lone pair of electron. Cl minus, Br minus, I minus, OH minus, Cn minus, even H minus. They have got a pair of electrons. Okay, simple anion that have got a pair of electron, not lone pair, that have got pair of electrons. So they have all got a pair of electron, and they are able to donate that pair of electron because they have it, and therefore they act as Lewis bases. Okay, let's come to another example. Molecules that are rich in electron. Molecules rich in electrons. Can you name some? See the compound, this benzene, it's rich in electron. So because it is rich in electron, it will be able to act as an electron donor. Look at alkene, it's rich in electron. Alkyne, rich in electron. So because they are rich in electron, they are able to donate electron, and therefore they can act as Lewis bases. Dear students, we have completed examples of Lewis acids and Lewis bases. We have seen that Lewis acids accept electron and Lewis base donate electron. Lewis acid we have seen examples, and Lewis bases also we have seen examples. Right? Now let us see some Lewis acid base reaction. Lewis acid base reaction, so that we get a better understanding. The first reaction is very familiar for us. This we have encountered in acid base reaction. Friedel-Crafts alkylation. Which is the Lewis acid? Lewis acid. Yes, because it accepts a pair of electron. And which is the Lewis base? Yes, this one, because it's donated pair of electron. Okay, look at the second example here. BF3 plus NH3. What happens? B, F, 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 N, H, 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 and positive, B negative. Positive because nitrogen has donated its pair of electron, and negative because it has accepted a pair of electron. So which is the Lewis acid? This is the Lewis acid because it has accepted a pair of electron. And what is the base? This is the base, Lewis base, because it has donated a pair of electron. Similarly, look at this example, zinc chloride plus H2O, zinc, Cl, Cl, O, H, H, positive, negative. Oxygen has got two lone pair. I forgot to write that in the first place. It has still got one lone pair of electron, but one lone pair has been taken by zinc. Therefore, oxygen become positive, and zinc, because it has accepted a lone pair of electron, it became negative. So which is the Lewis acid here? This one, because it has accepted a pair of electron from the oxygen. And which is the Lewis base? Yes, no doubt, that one. Dear students, I hope you have understood, and I hope you will like the class. If you have done so, if you have liked the class, please do not forget to subscribe this channel. Share it with your friends and like this video. Thank you very much.